All right. So, like in the previous talk, I will talk about tensors and also, group actions on tensors. So, my background is sort of invariant theory. So I'm particularly interested in things that are invariant under group actions. Now, a wheeled prop is some kind of algebraic structure that I will explain later. And prop is actually something that came from, I think, algebraic topology, which is a kind of abbreviation of the, products and permutation category. All right. So this is the setup. I start with a field K of characteristic 0. You may think of the real numbers or complex numbers. And I just fix one n-dimensional vector space. So, and then I look at tensors that lie in, say, a default tensor product of V. So that's what this notation V tensor D means. So then on this, we have a natural action of, the general linear group, oops, that goes too fast. Let's see. Let's go slowly. In particular, we can also look at the dual space. So we can take the tensor product of, say, P copies of the dual space and Q copies of V. And so a tensor I will just use write a tensor as a diagram. So every copy of the dual space, I think of it as an input, and every copy of V, I think of it as an output. Okay, so these are, these kind of wiring diagrams, and people, working with tensor networks use these kinds of diagrams also. Although in my setup, for now at least, I will make a distinction between V and its dual space. Because if you consider the action of GLV, they're not the same. So one can study like tensors sort of, what can you do with tensors, right? So there's a lot of structures that you can, do with tensors. So for example, if you have two tensors, you can take their tensor product and you get another tensor. So that's one way of constructing new tensors from old ones. So in a diagram would be kind of look like this here. There's also this one. So if you look at this here, so the tensor product of two tensors in the diagram, I'll just draw both diagrams and just think of it as now kind of a new tensor. So that's, and the other thing is we can do contractions. So if I have a tensor, right, so there's a natural pairing between V and its dual space. So if I take one output of a tensor, then I can contract that output, so to speak, with one input. And so if I had P inputs and Q outputs, then after the contraction, I will have P minus 1 inputs and Q minus 1 outputs. So in terms of diagrams, right, if T is a tensor that has 3 inputs and 4 outputs, then I can connect, for example, the second output to the third input. So that will look like this. Okay, and these contraction maps, I denote them by delta. And then there are also, special tensors, kind of trivial. If you just take 0 copies of V and 0 copies of V dual, then we just think of this vector space just, the base field K, which has a special element 1. And also, if you look at V dual tensor V, then we can identify this with, AND V, the space of endomorphisms of V. And there is a special element, which is the identity transformation. Okay, so that is a tensor that has just one input and one output. But I will use the convention instead of writing like it here in this box here. I often will just write just a straight arrow here. This is because, well, we have, for example, this relation. If you take the identity, two copies of the identity, and then I connect one output with the input of the other one, which is kind of contraction. That's basically just composition of linear maps. Then you get identity again. So another thing that we can do for these tensors is, you can permute tensor factors, okay? But in principle, you can achieve that also by doing taking tensor products with the identity and then contractions. So if you have a bunch of tensors, then we can create a lot of tensors by using tensor products, contractions, and maybe using the identity. And so you can, you have a very rich structure, basically. So here is some more examples. If you have two endomorphisms, which are tensors, right, which have one input and one output, then I can connect one output with the input of the other. And basically, what that means is that's exactly the algebra structure of AND V. So then you get the product. Now, if you have an endomorphism, you can also just do the contraction itself on this one matrix or endomorphism. And what you get is just a trace, right, of this linear map. And you could also take the trace of the identity, which would be just one loop. Well, trace of the identity is just the dimension of the vector space. So that's, in this case, n, if we started with an n-dimensional vector space. All right. Now, on this VPQ, right, we have this, which was, the tensor product of P copies of the dual space and Q copies of V. We have this action of GLV on it. And all the things that I've talked about, are sort of invariant under this action. So in particular, the one element and the identity, they're invariant under the GLV action. For example, GLV, acts on AND V by conjugation, and the identity is invariant under that action. And these operations that I have, such as the tensor product and these contractions, they also respect the group action. So I could first, if I have two tensors, I could first let the group act and then take the tensor product, or I could first take the tensor product and then let the group act. Well, that would be the same. So these operations are what I call GLV equivariant. And so one thing I'm particularly interested in is invariant tensors. So if you have some group, maybe not GLV, but some subgroup, then we can look at all the tensors that are invariant under this group action. And so so the following theorem is very classical, although I kind of translated it now to this particular language. So essentially, this is the first fundamental theorem of invariant theory, which basically says what are the invariant tensors for GLV. So, and it turns out if P is not equal to Q, then there are no invariant tensors, right? And that's already clear if you just look at the action of, say, lambda times the identity. Now, if P is equal to Q, then there are actually a lot of invariant tensors. And basically, you can think of these invariant tensors as sort of permutations, right? So, so whenever you have V and V dual, then inside the tensor product, you have the identity. And you can sort of, if I have several copies, then you can, match the inputs and outputs, but you can do this sort of an arbitrary way. So for every permutation, you get like a tensor. And the first fundamental theorem of invariant theory says that basically this way you get all invariant tensors. Now, in some cases, if the dimension of V is small, then it could be that these tensors may be linearly dependent. And in fact, we also can say, which is sort of the second fundamental theorem, exactly like how they are dependent on each other, if they are dependent. Okay, so summarizing, we have this basically the structure. So we take all these VPQ together. So that gives you sort of a bi-graded vector space. And that's also an associative algebra using the tensor product, where the tensor product is multiplication that's not commutative, but it's associative. And we also have like a one element for this multiplication or unit, which is just one. But on top of that, this V has more structure because we also have this, the contractions, and we have another special element, which was the identity. So this is basically a structure which is called a wheeled prop. I'm not going to give the precise definition of wheeled prop because that's somewhat complicated. But roughly a wheeled prop is, say, a bi-graded associative algebra with unit together with a special element, which is the identity. And these contractions and these things should all satisfy certain axioms. So this is somewhat like an abstraction of looking at tensors. So basically this sort of captures the structure of tensors where you consider contractions and tensor product, etc. So one example that we just saw is just, if we take all the tensors, the space of all tensors, right, for all P and Q, then that space has the structure of a wheeled prop. But there are other examples. For example, if I have a subgroup G of GLV, and then I can look at all the G-invariant tensors. And that's also a wheeled prop, because if I take, for example, two G-invariant tensors, the tensor product is also a wheeled prop, and same for if I do contractions, etc. So, so for that reason, if you're studying if you're studying invariant theory, in particular, if you're studying invariant tensors, then this wheeled props are sort of the most natural thing one could think of, in terms of structure. Now, these wheeled props were introduced by Markl, Merkulov and Shadrin in 2009. They weren't really thinking in terms of invariant theory, but anyway, so they had other things in mind. That's also why they, thought of it as sort of props, which is another structure where you don't have these contractions. But with the contractions, you kind of form these loops, so which they think of wheels. So that's why they call it wheeled props. But anyway, I think it's a terrible name, but fortunately they named it before me. Or in fact, I did name it, but not in a published paper. So then I was too late. So here's a nice.
What was your name for that?
Sorry. I just called. Well, I didn't really have a good name for it. I just called it Blackbox Algebra because I thought of these things as black boxes. But I think there may be other things already named Blackbox Algebra, so that might also not have been good. Here's some nice results of Schrijver. So that's for the case where, well, so I formulated it now in terms of real props. He didn't, but anyway, in this language, what he proved is the following. Suppose we work with the complex numbers, and V is a Hilbert space, so we have like a Hermitian form on it. Then we can also, the V is then isomorphic to the dual space, and we can identify. So there's sort of this map from VPQ to VQP using this isomorphism. And so now the following is true. So this is somewhat like a converse, right? So before we saw if you take the G-invariant tensors, then that's the subreal prop. But the converse is in this situation is also true. So, well, with some modifications. So if you have a subreal prop, which is just a real prop that's, which consists of subspaces of V, if it's also closed under the star operation, which is more or less, kind of like a complex conjugation, using the Hermitian form, then the subreal prop is actually of the form, taking the G-invariant tensors, where G is, say, a compact closed subgroup of the set of unitary matrices. Okay, so it's almost the way he thought about it. I think it's sort of like is kind of like Galois correspondence. So you have different subgroups on the one hand, and then on the other hand, you have these kind of subreal props. Well, he didn't call it that, but anyway. So that's over the complex numbers. So I'm not sure if I mentioned it. So I did write on the slide, but so this is all joint. Most of what I'm saying is going to be in joint work with Visu Makam. So here's a somewhat similar version, but not assuming the complex numbers. So it's a slightly different statement. So if you have a subreal prop, right? So that's just a bunch of subspaces that are closed on all these operations, and that also contain the identity and one, etc. So the most natural thing you can think of. If you have like a subreal prop, and so we have this natural pairing between VPQ and VQP. These two spaces are dual to each other. If we restrict it to this subreal prop, if that is non-degenerate for all P and Q, then the subreal prop is again taking the G-invariant tensors, where G is now a closed subgroup of GLV, a closed reductive subgroup of GLV.
Harm, we have a question from Josh.
Yeah.
He asks, are these theorems somehow related to the fact that star-closed matrix algebras is semi-simple?
I would say probably yes. Yeah. So, for example, this condition, this theorem here, this condition in for example the version of Visu and I, what this condition kind of means that there are no non-trivial ideals. So one can define what it is to be an ideal in a wheeled prop. And this condition kind of means that the only ideals are just zero and the whole the whole space. Yeah. So
Okay, Peter has a follow-up question. In the case over C, the complex numbers, the pairing is positive semi-definite, right?
Yeah, I didn't say that, but yeah.
Okay, I have a more mundane question. Could you scroll a little bit up so that we see the Schreiber theorem and your theorem next to each other so we can compare them? I think that is sort of what I should do, right? In some way.
Yeah. So this theorem, like this non-degenerate, is kind of automatic, since this pairing is then also going to be positive definite. So if you start with something that's positive definite and you restrict it to some subspace, it's again positive definite, right? So that's how the Schreiber's theorem would follow from our theorem.
Okay, yeah.
Is that good? Can I move on?
Yeah, you just seem to have answered it. Schreiber's theorem is a special case of your theorem. Is that what you're saying? All right, thanks a lot.
I mean, well, we can easily deduce it. So, as I mentioned, for these structures, one can define, homomorphism between real props, ideals, prime ideals, maximal ideals. So these notions are a little bit stronger, right? So, for example, ideal is not just an ideal as an associative algebra, but then it should also be closed under contractions. And yeah, well, I think that's it. And well, one important notion is also looking at subalgebras. If you start with some tensors, then you can look at the algebra generated by these tensors. The smallest sub-real prop that contains these elements. But I should say these, in general, real props are sort of more abstract. So the examples that I gave, they come from vector spaces, but it's sort of an abstraction. So that means that not every real prop comes from vector spaces. Just like the notion of a group, right? You can think of groups as subgroups of GLN for some n. So these are groups that have a representation, but you could also define a group more abstractly with just some axioms. But then it's not necessarily true that you can interpret these group elements as endomorphisms on some vector space. So in this category of real props, right, there's sort of an initial object. So if you think of like commutative rings, there's one commutative ring that, let's say, think of commutative rings with one. There's one commutative ring that sort of maps to every other commutative ring, namely the integers, right? So the integers is sort of an initial object in the category of commutative rings with one. And so a similar object exists for real props. So this is sort of this is a real prop for which there's always a unique homomorphism to any other real prop. So it kind of plays the important role in this theory. For example, ideals in the integers play an important role, right? So, or for example, prime ideals are given by prime numbers and 0, that determines the characteristic of a ring, right? So this Z here plays a similar role, and so it's kind of important to understand, the ideals in this initial object. So what is this curly Z? So basically, this is sort of like the free real prop that's generated by no tensors. But I say no tensors, but you always have one tensor, namely the identity tensor, and you also have one. So what are all the tensors that you can make with just the identity? Formally, what can you make? Well, you can take you can do a contraction, then you get a loop. But now, since it is all formal, this loop will not be some number, but it's sort of just an indeterminate inside Z. And then we also can form all these permutations. So it turns out this this initial real prop Z is a bigraded vector space, but it's actually only non-zero when P is equal to Q. And in that case, it's basically the group algebra for the symmetric group SP with coefficients in sort of polynomial ring in one variable.
Harm.
Yes.
We're sort of you got sort of 5 minutes, 6 minutes left since we asked a question in between.
Okay, thank you. So one result that Visu and I proved is we have a sort of a complete classification of all ideals, all prime ideals and maximal ideals inside the Z. So if we go back to the example before of this V, where V is an n-dimensional vector space, and then you can look at this set of all tensors that lie in products of V and V dual. So there's a kind of unique map that, the loop will map to N. So in other words, if I look at the kernel of this map, it will contain the loop minus N, where N is the dimension of this vector space V. And also, this is something more complicated. So for every permutation, I use this sort of abbreviation. If sigma is a permutation, that's just, the tensor that sends 1 to sigma 1, 2 to sigma 2, etc. Right? And so then you can take the skew symmetrizer of size n plus 1, which is, you can think of as the projection on the on the n plus first exterior power of V. And if V has dimension n, then that exterior power is equal to 0, and that's why you have this relation. And so these are exactly all the relations that you get. And so this is one example of a prime ideal. Or in fact, it's actually a maximal ideal. So here are the description of all prime ideals and all ideals is somewhat more complicated, but all maximal ideals are basically the ones that I just showed, but you can also do, instead of this Q symmetrization, you could not put the sign of sigma here. And this loop could be equal to negative P, right? So you can think of this as sort of a negative dimensional vector space. Anyway. But there are actually also models that one can construct. And then there are also prime maximal ideals that basically say that the dimension is equal to alpha, where alpha is not necessarily, or is not an integer. And so we have here another converse. This result says that if we start with a real prop, and so P is an arbitrary real prop, and so there's a unique map from Z to P, that's always true. And suppose that these things lie in the kernel, so that this loop is equal to N and this Q symmetrizer is equal to 0 inside P. Well, if that's the case, then P is essentially, again, a subalgebra of V, where V is an n-dimensional vector space, where we extend the field K to some commutative associative algebra A. So it's natural to give this the structure of a wheeled prop. So this is sort of a general theory. Now, it also has, specific applications, although, I don't have enough time in my talk to talk about this. But I may, well, first of all, maybe I say a couple of things here. One generalization, which is kind of for many people here might be very natural to do, is identify V with its dual. So if V is a Euclidean vector space, we have a positive definite bilinear form or Hermitian form, if you work with the complex numbers. Then we can identify V with its dual, and then so instead of arrows, we might kind of forget about the direction of the arrows and just identify V and its dual space. Another thing is, so here I started out with just one vector space, but one could also start with several vector spaces. And then to distinguish these different vector spaces, basically you get a theory where you have diagrams with arrows, but the arrows may have different colors. So if you have D vector spaces, then different vector spaces correspond to different color arrows or edges if you work, say, in the undirected setting. So now, so I'm almost, maybe I'll just say one application. If, for example, if you take, so this is something that we've looked at. If you take a tensor product of three vector spaces, let's call them R, G, and B, which correspond to the colors red, green, and blue, and you have a tensor, then, and let's say we have inner product on these spaces, so we kind of work with the orthogonal group rather than with GL, with the general linear group. Then the diagrams consist of, then the tensor can be viewed as a diagram where you just have three edges, but the edges have three different colors. So in a different work together with Derksen, Grayek, and Shadrin, we did some computations, for example. So to make this kind of relevant for this conference, you could, for example, compute the following. You take a tensor and you take the inner product with a simple tensor of length 1, and then you integrate this inner product. You take the 2d power and you integrate this over the product of spheres, and then you take the dth root of that. Well, if d goes to infinity, then this converges to the spectral norm of a tensor, and this spectral norm is difficult to compute. So having approximations that we could easily compute would be very useful. And so we did this calculation, and then here I stop here. So for example, if you take the 4th power and we integrate that, then up to scalar, we get sort of this combination of these diagrams. So with these colors, we call them like colored Brouwer diagrams. But so maybe I'll stop here because my time's, sorry for going maybe slightly over time.